All right, we're going to look at the last lecture in Unit 5, and it says 1 in a Mollion. It says if a million people say a foolish thing, it is still a foolish thing. So when we're looking at this, our learning objectives for this lecture, the students will understand the historical origin and the necessity for the mole. And then we'll convert between grams, moles, and number of particles. That would be number of particles would be molecules, atoms, and ions. And this is what we're trying to learn in this lecture. So what we already know, that ions combine to form ionic compounds. So we've been looking at ionic compounds, and they form to become more stable, and they either give electrons or they take electrons. They transfer those electrons to make those ionic compounds. Now, ionic compounds are extremely small. We know that they're really small. If we talk about it, when we're looking at all the different sizes of it, they're incredibly small. Now, it is difficult to experimentally manipulate individual atoms, ions, and compounds. So in a lab, we don't go in and just experiment on one atom. We don't just go in and experiment with couple atoms. We experiment with lots and lots of atoms. So what we learned in the lab, the mass of the individual pieces and number of pieces can be used to estimate the mass of a whole. And an empirical formula is the lowest whole number ratio of atoms in a molecule, and that a molecular formula is the ratio of all atoms in a molecule. So how many salt molecules are in the salt container? Now, the number of salt molecules varies depending on temperature, atomic size, and pressure. So when we're looking at this, volume is not a very good indicator of the amount. And so if not volume, we need to find a way to express a large number of particles. So when we're looking at this, we can express things in pairs. So if I say I have 2 pairs, well, I'm really talking about 4 things. The actual number would be 4. If I say that I have 2 dozen, well, I'm looking and I'm saying I actually have 24. My actual number is 24, but it's just 2 dozen. And if I say I have 1 gross of something, that really means I have 144 things. So why don't we use these to express the number of molecules? Well, when we're looking at molecules, molecules are extremely small. So a very small amount of a substance is an astronomical size of actual molecules. So Avogadro did experiment and analyze gas. He developed this number by looking at different gas volumes and different particles. Now, the mole is really defined, so when we're talking about the mole, it is defined as the number of atoms in 12 grams of carbon, and specifically 12 grams of carbon-12. So 1 mole of tennis balls are 6.02 times 10 to the 23rd tennis balls. That's Avogadro's number. So just like saying 1 dozen tennis balls, guess what? That's 12 tennis balls. Well, Avogadro's is just a bigger quantity. It's 1 mole of tennis balls is 6.02 times 10 to the 23rd power of tennis balls, which is an astronomical amount of tennis balls. So if we're looking at our first question, it says how many water molecules are present in 2.4 moles of water. So when we're looking at this, what we can say is that, well, Avogadro's number is essentially a conversion factor. 1 mole of anything equals 6.02 times 10 to the 23rd of anything. And in this case, we're talking about molecules. So what we can say is that 1 mole of water molecules, so H2O, equals 6.02 times 10 to the 23rd molecules of H2O. So when we set this up, we just start with a number that we're given, 2.4 moles, and we do what we call dimensional analysis. So we set it up. Now, the one thing you want to think about is whatever unit is right here, that's the unit that has to go down here to cancel out. So you see how this says moles? Well, guess what? That says it right here in our conversion factor. So we'll put that guy on the bottom. And then what we do is we put the other half on the top. And that's how a conversion factor works. And we can flip this if we need to, but guess what? We want it this way because we want moles to cancel out with moles. And remember, this is molecules, which is what we want. So we go 2.4 times 6.02 times 10 to the 23rd, and we will get something right around 8.4 times 10 to the 23rd molecules of water. And that's what we will get, which is an astronomical amount. It's a big number. The next thing, it says the average mass of a baseball is 145 grams. Determine the mass of 1.4 moles of baseballs using dimensional analysis. So this one's a little bit harder. So we have 1.4 moles of baseballs. Well, we know we just did a conversion where we said 1 mole of anything, and this is just baseball, so I'll just put B, equals 6.02 times 10 to the 23rd baseballs. So when we're looking at this, what we can say is, well, moles and moles, set it up. 1 mole of baseballs is 6.02 times 10 to the 23rd baseballs. Now, in dimensional analysis, what we can do, the other thing is that we know that 1 baseball is 145 grams. So 1 baseball equals 145 grams. So when we're looking at this, remember, this is unit cancels out. Moles goes away. What unit is this? Well, that's baseballs. Well, we know that 1 baseball equals 145 grams. And so then all we have to do is, since all the units canceled out, we just multiply the top. So multiply these guys, multiply, and then divide by what's on the bottom. So 1.4 times 6.02 times 10 to the 23rd times 145 is going to give us a number of 1.2 times 10 to the, there we go, times 10, write that again, times 10 to the 26 grams, all divided by 1 and 1. So if we divide it by 1, guess what? It's just the same number. So that is how many grams 1.4 moles of baseballs have. Now, to do this with atoms, what we have to do is we need to know their mass. Just like we need to know the mass of the baseball, guess what? We need to know the mass of atoms and how much are in each one. Now, the atomic mass, which is on the periodic table, you can find it on the periodic table, it's down here, it's your atomic mass, is used to convert between mass and moles. And we call this our average atomic mass. So it's the average mass of all the naturally recurring isotopes. So we find this on the periodic table. So anytime we're using mass and talking about elements on the periodic table, 1 mole of, this case we have boron, equals 10.86 grams of boron. So 1 mole is always going to equal the mass on the periodic table. So, a mass to moles conversion. The atomic mass of any element is the conversion factor for moles. This is called the molar mass. So, when we're looking at the molar mass, it's the mass of 1 mole. So when we're looking at this, say I have 1.8 moles of boron, and I want to know how much mass that is, so how many grams that is. Well, we look on the periodic table, 1 mole is 10.8 grams. So 1 mole equals 10.86 grams. And look at what we did. We put moles on the bottom to cancel out that unit. That goes right there. And then our 10.086 grams goes on top. And we see that their units cancel, and we find out the mass of a mole of boron. So, in looking at this example, it says that a 100-gram sample of calcium is dissolved in a 10 liters solution of water. Calculate the moles of calcium in solution. So we want to calculate the moles of this 100-gram sample. So what we do is we take this, and we know that 1 mole of calcium is going to equal its molar mass on the periodic table, which is going to be 40.078 grams. So we set it up. We have 100 grams of calcium, and we have our grams sitting right there. So guess what? We're going to put our grams on the bottom, and we're going to put our moles on the top. And then we go ahead and we work this out. 100 times 1 will give us 100. 40 times, just by itself down there, is 40.078. We go ahead and plug this in the calculator and we'll get rounded right to 2.5 moles of our calcium. Look at our next one. It's a little bit harder. It says how many moles of copper 1 sulfate are in 2.4 grams of copper 1 sulfate. So practicing just a little bit, going back to ionic compounds, and the reason why we have to do this is because this is not an element on the periodic table. So we got to figure out its formula. So it's copper 1. So we write copper, and then we write sulfate, SO4. It's a polyatomic ion. So copper is going to, since it's copper 1, it's plus 1. Sulfate's minus 2. It's a polyatomic. We swap and then drop them down. So we have Cu2, SO4, and that one would just go there and we'd erase it. Now this is important because we need to find the mass of all of these atoms, or all of those moles. So to do that, we look at how many we have. Copper, we have 2. Sulfur, we have just 1. And oxygen, we have 4. And then we multiply them by their molar mass on the periodic table, which copper is 63.55. Sulfur is 32.07, and oxygen is 16. So we multiply these out, and then we add them up, and we'll get a molar mass of 223.15 grams of copper sulfate. Well, it still means the same thing. 1 mole of copper sulfate, that guy right there, equals 223.15 grams. So we set it up. How much are we starting with? 2.4 grams. So 2.4 grams of copper sulfate. Grams is on the top. Guess what? That guy is going to go on the bottom. And then the rest of it goes on the top. And you see that our units cancel, and we're left with mole. So when we do this, we'll get 0.011 moles of copper sulfate.